Hello and welcome to another video in this series on derivatives. Here we're going to look at an application. We will be asked to solve a problem involving concavity. So obviously we need to look at this concept. We'll also be looking at the concept of inflection, in other words inflection points, and we'll also be going over relative maxima and minima. So here in this diagram we see a region here where the function is concave upward, and here we see the region in which it is concave downward. Here is the problem. We were asked to find the regions in which this function is concave upward and where it's concave downward. Note, you are expected to be able to solve these problems without having a graph of the function. However, to make this explanation somewhat better, I am first going to look at this using graphical software, so that you understand clearly what it is that we're looking for and how we can use derivatives to then answer this question. After we have done that, we'll then go back and do this problem again as you'd be expected to do it. Okay, so first here is a graph of this function. As you can see, in this region it's concave upward, and in this region it's concave downward. So we could shade this in, and if you look at this graph carefully, we can see that this value is 0.5. So we can answer the question immediately. We know then that this function is concave upward from negative infinity all the way up to and not including 0.5. And it's concave downward from 0.5 all the way over to plus infinity. The domain of this function goes on for all infinity. So it's going to be concave downward from x equals 0.5 all the way to infinity. And here it's going to be concave upward from 0.5 all the way to negative infinity. So again, this continues on for all eternity. Let's see how we can use calculus and more specifically derivatives to answer this question. The first thing we're going to want to do is find the relative maxima and minima. Why? Because where there's a relative maximum, we know in that region it's going to be concave downward, and where there's a relative minimum, the region is going to be concave upward. So how do we find these critical points? Well, we simply look for where the derivative is 0. In other words, where the gradient of the function is 0. And so I have drawn here a graph of the first derivative. So this graph is giving me values of what? The gradient of this graph. So I look here and I see right here where it crosses the x-axis that the gradient of this graph will be 0. So this is the point 3 and this is the point minus 2. The gradient here is also 0. Notice this is cutting the x-axis here. How can I tell if this critical point corresponds with a maximum or a minimum? Well, I look here and I see the gradient goes from being positive to negative. So then here I must have a maximum. I can also see it here that the gradient goes from being positive to negative. I can come over here and I look and I see that the gradient goes, as I move to the right, from being negative to being positive. So then I must have a minimum here. If you look at this function, notice the values under here are negative and the values up here are positive. But instead of testing points on both sides, we can look at the derivative of this function, in other words, the second derivative of this one, because we are interested in noticing then whether or not the gradient is increasing or decreasing. Notice here, right at this point, we have an increasing gradient, and right here at this point, we have a decreasing gradient. In other words, the gradient of this function here, of this one, is positive, and the gradient of this function is negative. So where the gradient of this function is positive, if that happens to be a critical point, then it'll be a minimum. And where the gradient of this function is negative, if that point happens to be a critical point, then that will be a maximum. So let's look at the gradient of this function, then, which is the second derivative of this one. And that's what we have here. So if we come here, we come here to this critical point here, and we see, oh, this value is negative, so this must be a relative maximum. And we come here and we see that this is positive, so then this must be a relative minimum. Now we need the point of inflection. We need to find the point where the concavity changes. So notice as here the gradient of this original function is 0, and it increases and then it starts to decrease. If we look at the gradient function, we see that it increases and then it starts to decrease. So what we want to find is where this gradient here is 0. In other words, where this line passes the x-axis, and as we can see here, it passes at 0.5. So that gives us the point of inflection, and so now we can tell then that this function will be concave downward from negative infinity up to 0.5, and did I say downward? It's going to be concave upward from negative infinity to 0.5, and then concave downward from 0.5 onward to positive infinity. Alright, so now let's look at see how we can do this then analytically, not using these graphs. So here are the steps we're going to follow. Now note, you don't necessarily have to follow it in this order. For example, you could find the point of inflection first and then find the relative maxima and minima. But let's do it this way here. So what I do is I find the first derivative. So again, remember when you're doing this, you won't have this graph, but I'm just giving this here so we can follow the logic of this. I find the first derivative, so I'm assuming you can do that, right? When I get the first derivative, I need to know where it's going to be 0. And so when I equate this to 0, I get this, and then I solve, and I can solve this easily and get 3 and negative 2. So you need to know how to solve these quadratic equations, either by factorizing or using a quadratic formula. So once we're here, well, I know that I have these two critical points, -2 and -22. So where do I get this -22 from? I simply put this -2 into this function here, and I evaluate it, and I get f of -2 is -22. And then I take this value 3 and find f of 3, and I get 40.5. So then I know where the critical points are. One is up here and one is down here. So now I need to know whether these represent maximums or minimums. They could also represent some kind of point some kind of stationary point, but that's not going to be the case here. So when I find the second derivative, notice I get -6x plus 3, and then I test this using these two critical points. I test it using 3 and -2. So when I test it using 3, I get -15. So since the second derivative there is negative, I know that's a relative maximum. So if you need to go back in this video and look at the reasoning for that. Likewise, when I test -2, I get +15. So that's a relative minimum. So then I know that these two critical points, this one here is a minimum and this one here is a maximum. And of course, given that, then I know that at -2, this region here is going to be a region of upward concavity, and over here at 3, this is going to be a region of downward concavity. So now all I need to do is find my point of inflection. So I go to my same second derivative, and now I equate it to 0. So again, go back and look at how we explain the reasoning behind this. So I find the second derivative and set it to 0, and I get 0.5. And so I know that the point of inflection is at 0, 9.25. Again, where do I get this 9.25 from? I simply put 0.5 here. In other words, I find f of 0.5, put these values in here, and I get 9.25. So that's the point of inflection then is going to be 0.5 and then come up 9.25. And that's it. I now can find these regions. It's going to be concave upward from negative infinity all the way to 0.5, and downward from 0.5 all the way to positive infinity. So what I want to do now is just take a look at how, say, a student would do this, without having this graph or anything. So here we have the problem written in my very horrible handwriting. So if I have this function and I'm asked to find the regions of upward and downward concavity, well, I already know I have to find the relative extrema. This just simply means maximum and minimum. And so I find the first derivative, set it equal to 0, and then solve. And I see, okay, my critical points are at x equal 3 and x equal -2. I get these y coordinates by simply substituting these values back in the original function. And then I know I'm going to need the second derivative to then determine if these are maximums or minimums. So I find the second derivative, and then I plug -2 and 3, and I notice that here I get 15, which means then I have a relative minimum, and here I get -15, so I have a relative maximum. So at this point then I'm able to draw a rough sketch, and I put this point here, and I know it's a relative minimum, and I put this point here, and I know it's a relative maximum. So at this stage, I would not have this yet. So maybe I shouldn't have drawn this yet. This would be blank. And now I would go and find this point because this is my point of inflection. So how do I find the point of inflection? I take the second derivative and equate it to 0 and solve. Notice I get x equals 0.5. And so then the inflection point will be 0.5 comma 9.25. Again, I get this 9.25 by placing x equals 0.5 in the original function. And now I can plot this point roughly. So I have this point here. And so now I'm capable of drawing a rough sketch now. And I know the region of upward concavity will be from minus infinity to 0.5 and downward concavity from 0.5 onward to plus infinity. And so that's that. So as you see, this shouldn't be something that's very hard. It's just that you have to be in control of something that's very abstract, especially at first. You know, you have to find a function, then you have to have the gradient. You have a function that gives you the gradient of the original function, and then you have another function giving you the gradient of that first derivative of that gradient function. So again, you have a function, you have to work with its first derivative, which gives you the gradient at points along this function, and then you have to work with the second derivative, which gives you the gradient at points along this function, and be able to use it to then, you know, come to some conclusion. Okay, so that's it for this video. I hope this was of some help to you. So okay, bye for now. Remember to subscribe. Bye.